All right, these are the notes for Algebra 2, Section 7.6. We're actually looking at the first part of 3 for 7.6. In this section, or in this part, we're looking at solving exponential equations. Now, an exponential equation is an equation with a variable in the exponent, right? For instance, 2 to the x equals 4 is an exponential equation because the x is in the exponent. Now this equation is actually pretty easy to solve, right? 2 to the x equals 4, so x has to equal 2. We have seen this before because we used that when we were evaluating logarithms. Well, we're going to look at processes that we can actually use to solve exponential equations that maybe aren't quite so straightforward. Now, the basic idea behind solving an exponential equation involves the property of equality for exponential equations. Now, this property of equality for exponential equations says that if b is a positive number other than 1, then b to the x equals b to the y if and only if x equals y. So that's actually pretty useful. Now, it seems a little confusing here, so let's look at an example to see how this would actually show up in a problem. For instance, if I had 5 to the x equals 5 to the 4th, well then, since I have a base, a term here with the base of 5 equaling a term here with the base of 5, I can ignore the bases. I can just pretend like they don't exist and say that x equals 4. And that would be the solution to the equation. Pretty simple. Let's look at how it shows up in maybe a slightly more complicated way. Now, let's undo that. Okay, so we want to solve an example 1. The equation 64 to the x power equals 16 to the x plus 1 power. Now, these two terms, right, we do have a term with an exponent here and a term with an exponent there. But what we don't have are two terms with the same bases. So our first job will be to rewrite each one of these terms so that they have the same base. Now, the best way to go about this is just to do a little bit of number crunching in our head and do a little puzzling and stuff like that. For instance, I know that 16 squared is a big number. It's not 64. So I can't change 64 to have the same base as 16. But I also know that 64 and 16 are both powers of 4. Right? 64 is 4 to the third. 16 is 4 to the second. So I could rewrite each of these with a base of 4. And that's what I'm going to do. 64 is 4 to the third. 16 is 4 to the second. And I've rewritten it, and now they have the same base. Now what you might notice here, of course, is that I have 4 to the third to the x power and 4 to the second to the x plus 1 power. Now we know, because of the power of a power property, one of those exponent properties that we used a long time ago and continue to show up, that if I raise a power to a power, I multiply the exponents. So 4 to the third to the x becomes 4 to the 3x. On the other side, maybe a little bit more complicated, I have 4 to the 2 times x is 2x plus 2 times 1 is 2. Right? I had to distribute that 2. Right? So 2 times x is 2x, 2 times 1 is 2. So on one side I have 4 to the 3x. On the other side I have 4 to the 2x plus 2. Now, of course, my bases are exactly the same. So according to the property of equality, I can ignore these 4s, these bases, and just look at 3x equaling 2x plus 2. Since the bases are the same, I can ignore them. Now, of course, I would want to subtract 2x from both sides to solve this equation. And I would end up with x equals 2. So the solution is 2. And if we wanted to check it, we could, of course, plug this 2 back into the original equation. 64 to the second power is 4,096. You type that into a calculator. 2 plus 1 is 3. So 16 to the third power is also 4,096. So the solution does work. Now, sometimes there will be no way for us to get the bases to be the same. For instance, in example 2, there is no way that we can get 6 to the x and 27 to have the same base. It's just not going to happen. So we have to go about it a slightly different way. And the way we want to go about this is to take the logarithm of each side. So we'll take the log of 6 to the x, and we'll take the logarithm of 27. Now, there are a couple of different ways we could go about this. The way that I think is probably best would be to just use the log base 6. So what I did was I said, all right, well, the base of this exponent is 6. So I'm going to take log base 6. And here's what happens. I do log base 6 of 6x equals log base 6 of 27. And magically, log base 6 of 6, of course, we know cancels out. Right? That log base b of b to the x equals x. Right? We did that when we were looking at inverses. So log base 6 of 6 cancels out, leaving us with x. X equals log base 6 of 27. Now you might be saying, oh, well, how do we do that? And you need to remember the change of base formula. We worked on that. The change of base formula says that if I have log base 6 of 27, that equals the log of 27 divided by the log of 6. So I can type that right into a calculator, and I'll end up with 1.839, or about that anyway. So the solution is about 1.839. Now, if I put that into, for x here, 6 to the 1.839 power, I would get about, not exactly, but about 27. It'd be pretty close enough for government work anyway. So this, taking the log of both sides is pretty convenient. It allows us to get rid of this exponent. Let's look at a slightly more difficult example. Here I have, I want to solve 6 times e to the 0.25x power plus 8. Now, there's a lot of stuff going on here, and we want to break it down and do it piece by piece so we don't try to get too much stuff going at one time. For instance, the first thing that we need to do is isolate the exponential term. So we want to isolate the exponential. That would be the very first thing that we do. Let me rewrite that so it looks like I actually know what I'm doing. That would be nice. There we go. So the first thing we want to do is isolate the exponential. To do that, we're going to subtract 8, right? Because the exponential is this guy here, e to the 0.25x. So we're going to isolate that. We start by subtracting 8 just like we would any other equation, giving us 6 times e to the 0.25x equals 12. We divide by 6, right, to get rid of that 6. Gives us e to the 0.25x equals 2. Now the next step that we would want to do is take the log of both sides. Keep in mind, we can't do this, we can't take the log of both sides until after we've isolated the exponential. So this, isolating the exponential, has to come first. Now when we want to take the log of both sides, we need to take the log base e, because e is our exponential. And log base e, of course, we know is ln. So we're going to do ln of e to the 0.25x. And that equals ln of 2. Now when we do this, of course, we know that the ln of e cancels out, leaving us with 0.25x equals ln of 2. All right, which leads us to the last step that we need to do, which is to solve for x. All right, so we have a three-step process here. We isolate the exponential, we take the logarithm of both sides, and then we solve for x. And solving for x involves mostly just dividing by 0.25. And even though it may not look like it, we can type this directly into our calculator. Natural log of 2 divided by 0.25 is about 2.773. So that would be our solution. Using those three steps here, which are pretty general, but they're useful, right? We isolate the exponential, we take the log of both sides, and then we solve for x, and we'll get an answer.